everyone. Well, it is such a privilege to introduce somebody whose work is shaping the future of computing. So Julian Kelly is the Senior Director of Quantum Hardware at Google Quantum AI, where he brings over a decade of expertise in designing and fabricating and fine-tuning semiconducting quantum processors, from many generations of Sycamore to the latest breakthrough Willow chip. Julian is one of the earliest members of Google Quantum AI. So welcome, Julian. It's great to be here with you.
Thank you so much. Really wonderful to be here.
And we will be doing Q&A at the end. So if you do have questions, you can save them for the last 10 minutes. Okay, so I'm going to start with the question I'm curious about. For the past 80 years, the world has been running on classical computers. And we've done some pretty remarkable things, arguably. I mean, everything we're talking about in AI, that's powered by classical computers. We've gone to space a few times on classical computers, yet we consistently hear that quantum computers will be the successor to classical computers. So could you explain the core concepts behind quantum computing? How is it different from classical computers? And why is quantum computing important?
Yeah, thanks. This is a great question. So classical computers can solve all these wonderful problems as you just described, but it turns out there are some problems that only a quantum computer can solve. So a quantum computer can solve certain problems that would otherwise be completely impossible for a classical computer. In terms of the kind of fundamentals of how they work, classical computers work on binary or bits. That's in 0 and 1. You can think of it as a light switch, as either in the on or the off position. But qubits use quantum bits or qubits. And qubits can be in what are called superposition states, 0 and 1 at the same time. And they have this exponential scaling behavior. So every time you add a qubit to your system, you can think of that as kind of doubling the computational power of your quantum computer. Fundamentally, quantum computers are able to run on quantum mechanics. And quantum mechanics is what underlies all the physical laws of the world. So quantum computers, in some sense, speak the natural language of the universe.
Okay, and we're going to get into that a little bit more. So would you consider quantum computing then to be the next big thing after AI, or is it more nuanced? Will quantum and AI converge in some way and end up reinforcing each other?
Yeah, it's a great question. I think it's a good mental model that quantum computing is the next big thing after AI. It's distinct from it, but at the same time, they do have the opportunity to complement each other. You can maybe think of that in two ways, like AI helps us with our day-to-day jobs in building a quantum computer right now, but also a quantum computer has the opportunity to enhance AI systems as well.
And we're going to get into some of the challenges with quantum, but I want to talk about some of the possibilities. So why should we all be paying attention to what's happening in quantum? What could theoretically become possible in a world with quantum computers?
Yeah, so there are a number of application areas that we've identified that quantum could be beneficial in. So, for example, a quantum computer could be critical in the drug discovery process. So, for example, we have a paper from a few years ago where we worked on this particular enzyme. It's called cytochrome P450 enzyme. And you could imagine if you're a drug maker, one of the things you do is you make all these different candidate drugs, you work hard to build all of them, and then you don't know how they're going to behave when they go inside the human body. Some of them get metabolized by this enzyme and immediately don't work, right? And the problem is you can't predict which ones are going to work or which ones aren't, because you would have to then understand what quantum mechanics is going to do. So a quantum computer would allow you to basically figure out which drugs would or would not be effective beforehand in simulation. And you wouldn't have to spend your time building all these candidate drugs for a number of them to immediately fail. You could just focus on the ones that are going to be more effective, which will just save time and money for everyone.
And I'm starting to sense some of that convergence with what's happening in AI and drug discovery, and then eventually being able to model that with quantum. Okay, so based on where the industry stands in this moment, when do you think quantum computers will actually be solving some of these problems?
Yeah, so that's a big goal for us, and we're optimistic that on the timescale of about 5 years or so, we could be able to solve a real-world, interesting problem on a quantum computer that would be impossible to solve on a classical computer.
So just after 2030, we'll give you a call and make sure it's all ready to go. Okay, so about a year ago, I was attending a conference, and I struck up a conversation with a professor of quantum mechanics, and he said something that I will never forget. He said, the more you learn about quantum mechanics, the less sense any of it makes. So in terms of the breakthroughs that we're waiting for and in actually building scalable, practical computers, is it breakthroughs in the hardware? Is it the software? Or is it understanding of this strange world of quantum physics?
Yeah, so there's maybe two parts to your question. The first one, I think it's so interesting that quantum often gets this like, oh, it's totally crazy, it's unapproachable, how could you really understand it? And I think what is so fun about being working on this project, and one of the things that really drew me in is the fact that you really get to interact with quantum systems yourself. Like when you're a student in undergrad or graduate school, you run all these quantum equations and it seems very intangible in some sense. It's like, oh, it's for things that are really small and really cold, you don't interact with. But when you actually have these quantum computers in the lab, you can play with them. Like you get to tinker with them. You actually can understand them and you can build an intuition. And it's super fun because then quantum mechanics becomes just like another tool in your toolbox. And it's a very engaging problem to work on. But going to the main thing that you're asking about, there's a number of things we need in order for a quantum computer to be useful. We need the hardware and we need the software. The history of quantum computing is quite interesting in that, in the mid-90s or so, people came up with these kind of application use cases to be like, oh, if only I had a quantum computer, I could do all this cool stuff. Yeah. But the hardware was, nowhere close to that kind of use case. So in some sense, the hardware really has limited a lot of the development of these quantum computers to be able to kind of make them performant enough to be interesting. That being said, it's a joint problem both on kind of bringing down the resource costs on the application and software side, but also building up the hardware to be large and performant enough to kind of meet in the middle until we really have that first real-world application use case.
And I think we have started to hear about progress more frequently in the last 18 months. We've been hearing from multiple companies, different breakthroughs or milestones, So for somebody who's not in the field, how should we decipher what's a breakthrough that matters and what is actually just hype?
Yeah, this is a really good question. And I'll say, even for an expert, it can be difficult to look in the media and decipher exactly what is important and what isn't. You really kind of dig into the details. But I can offer maybe 3 points of guidance that people can ask whenever they're looking at some type of announcement to get a sense of how important it is. So number one, at the end of the day, we're building a computer. It might be a computer that runs on quantum mechanics, but it's a computer. And computers have spec sheets. They have how big is your computer, how fast does it run, how does the information move around, how's the connectivity. And you can use this to sort of cut through these big hypey announcements and say how powerful is the thing that you built. So for example, recently in December, we had this announcement of our chip Willow, and we very deliberately attached a sort of specification sheet to be like, here's all the numbers that we think that you need to know to understand what this computer has the capability to do. And that's a sort of guide that when you see something else, you can say, okay, well now tell me a bit more about it. If someone, that'll just sort of help ground you at the end of the day. Number two is the sort of, will it scale? Like some demonstrations are kind of small, foundational things, but at the end of the day, we want to build a large scale computer. And the third thing is, at the end of the day, the competition for a quantum computer really is a classical supercomputer. So if you're running something on your quantum computer, but you could also do it on a classical supercomputer, why should you care, right? That really, for us, is where we feel the bar is. We need to solve problems that otherwise would be completely impossible on our quantum computers, or we don't think that we've done our job.
I see. Okay. So now we know what counts as hype and to follow that spec sheet. So Google recently achieved a significant milestone in quantum error correction with its Willow chip. So can you provide some context as to where this places Google in the global landscape of quantum computing and why this breakthrough was quite pivotal on the journey to scalable and practical quantum computers?
Yeah, so we're really excited about this breakthrough in quantum error correction. And what we're able to do with our Willow chip is meet an outstanding challenge that's been in the field for 30 years. And what that is that when this theory of quantum error correction came out in the mid-90s, the thing that's tricky about it is you actually have to make the hardware good enough in order for it to work. There's a threshold that you have to cross, otherwise it won't solve your problem and you can't make a machine that's large scale. So in terms of maybe an analogy to make it a bit more accessible, Imagine that there were a whole bunch of companies or teams trying to get into the aviation industry, right? Like suppose no one had ever built a plane before, and you might have a plane over here. It's like this one's got 2 engines. How cool is that? This one's got 2 floors and like first class, and that one's got like a cargo bay, and everyone's talking about how we're gonna fly people all over the world and do logistics and stuff like that. But the planes need to fly at the end of the day. They need to be like sustain flight. And in some sense, this is showing that Willow, this chip that we made, can actually do that in the context of error correction. It can sort of pass this threshold of liftoff and sustaining its flight. And that's really a foundational requirement in order to build and scale up to larger computers.
Really helpful analogy. Okay, so in the world of AI, we hear a lot about AGI. That is the kind of holy grail moment. It is the moment where everything changes. Is there a particular moment in quantum that would be considered the AGI moment of quantum where everything changes from that point forward?
Yeah, I think a moment that you could look to that would be sort of an undeniable breakthrough is that if you can solve this, a practical real-world application, and then do that on an error-corrected computer. And the reason that this is so important is you've crossed this 0 to 1 moment of quantum computing, because you've not only got a real-world application, but you've done it on this foundation that can then be incrementally improved and will go into the future, starting up, you could imagine like a virtuous cycle or kind of a Moore's law for quantum computing in that case, be much more like predictable and understandable and reliable. And I think at that point, it would be undeniable that this new computing paradigm is here. It can do things that are useful, and we can see how it's going to move into the future.
And is there an acronym? Is there a QGI somewhere that we can find?
That's a great question. I don't think we have or I'm not aware of a cute nickname for that yet, but we should probably get one.
Okay, and so how can the average person expect quantum computers to be a part of their life? Like, am I on my laptop and then I go into a quantum application or a problem that's unique for quantum computers? Or can we expect a line of quantum-first devices in the pipeline?
The way that we're thinking about it right now is that you kind of have to rewind yourself a number of decades on the classical computing front. Like we're kind of building, in some sense, these like quantum mainframes that people would dial into originally for like kind of specialized problems, right? So we talked a bit about the drug discovery one. Quantum computing also has applications in, for example, optimization as potential benefit. There's other cases like in industrial chemistry, like in fertilizer production, it could greatly enhance the process to make that reduce the amount of energy. So the initial use cases that we have targeted are very like focused on these like big scientific and industrial questions. That being said, I think that if you were to ask someone in the 50s or 60s or 70s about like where you thought computing was going, I don't think anyone would have predicted, the type of technology that you see around us today, or like was, just shown off here as well. So that's sort of like a couple steps in the future. I don't know of any like super clear use case to say one way or the other, but I think it's a good mental model in terms of where we are in quantum computing as compared to like looking at the history of the development of classical computing.
Because famously, Andy Grove, CEO of Intel in 1992, said the idea of a smartphone was nothing more than a pipe dream fueled by greed, and now here we are.
And there's a nice quote, I think, from IBM at some point in the 1900s about, we think that there's only like a desire for 5 computers in the entire world, which is, that's clearly not where we're at today.
Meanwhile, computers driving us around now. Okay, so a big question, are quantum computers going to break the internet? And if so, or break encryption? And if so, what should every government and every holder of Bitcoin be doing today to prepare for what experts call Q-Day?
Yeah, so I think the kind of application to encryption has been something that's been known for over 30 years at this point. It was discovered in the mid-90s. And I think the fact that you're asking me about it is actually really great evidence that this is sort of a well-understood issue. There are government institutions like NIST, for example, that are leading the way in developing post-quantum cryptography protocols. And I think we're working to support them. We're collaborating with them. And I think it's important that we get those sort of rolled out to everyone. That being said, in terms of maybe an analogy, one to think about is something like Y2K, where people were really worried about this. some people are thinking, oh, planes are going to fall out of the sky and like the whole world's going to shut down. But people were very aware of the issue, and then people did all the prep work, to kind of get everything in order. And then like when it actually came, is a bit of a nothing burger, and it's a little bit of a butt of jokes at sometimes. I mean, you have to do the preparation for it, but that's a kind of example to keep in mind.
So December 2029, if you are holding Bitcoin, you might be able to still hold. Okay, so we've established quantum computers. They are coming eventually, and that we do have to do some migration for the post-quantum world, the post-world of encryption. Who is responsible for preparing the world for this, especially a problem that spans governments, industries, and billions of devices? Who's actually overseeing this?
I mean, I think we're really looking again to like leadership from institutions like NIST to kind of like help set the standard, and then we can support that in any way that we can in terms of like product integration, for example, of things that we've already started to work on. But I think that's where we look to. Okay,
so it's kind of in collaboration with the academic side, with the government side, and with the private sector.
That's right.
Okay, so in a recent blog post published by Google, it was written that quantum computers could one day prove that we may live in a multiverse. So in your opinion, do we? And if so, what do quantum scientists know that the rest of us do not?
So this is sort of like a very fun question for quantum physicists that goes back about 100 years or so. This is like the 100th year of quantum that we're celebrating this year. And one of the things that this fundamentally stems from is that there's this, it seems in some cases like there's sort of two rules that govern how quantum systems work. Like you just sort of use one set of equations and you do like a measurement at the end, and we call it like the measurement problem. And what this does is like we know extremely well how quantum systems work. It's one of the best understood and measured theories in physics. It's been tested very rigorously in all these different applications. But there's this sort of like one key point where it's left up to interpretation. And so like one of the interpretations is called the many worlds interpretation, there's the Copenhagen interpretation, and there's others as well. My personal taste is I'm very much an experimentalist, and if I spend my time thinking about things that I can construct a very clear hypothesis for. So like until we're kind of at that moment, it's, I would say honestly, for me personally, not something I think about that much, but I know a lot of other people really enjoy the kind of philosophical debate of what quantum mechanics means.
Yeah, I think a lot of people inferred because Will-Chip helped to solve a problem that would have taken a classical computer longer than the age of the universe to solve. Well, therefore, it must prove that there's some multiverses going on. But I guess that's up to the beholder in terms of how they're interpreting that.
Yeah, and I mean, I think it's also just like another really good test of quantum mechanics because honestly, before we were able to start doing these demonstrations, people still had these suspicions that, hey, maybe when you get a really big, controllable, fine-tuned quantum system, you were going to start to see some deviations from the underlying theory. And, that was just sort of a hunch or a concern that people had. And, we haven't seen that. In fact, we just have more evidence that quantum mechanics works the way that we think it does, which is really, it's pretty interesting.
Mm-hmm. Alrighty. Thank you so much, Julian. This was a pleasure.
Thank you
all.